Hello! This is going to be the last video for this section, and it will round out Chapter 5. I hope that you have been able to stay on top of this material that we've talked about, characteristic equations and exponential solutions. And in that last video, talking about how exponential solutions can actually lead to sines and cosines if those solutions are complex. Here we're going to extend it to higher order equations, but this is actually usually a section that is left for students to do on their own. So this is actually kind of special. I'm not used to doing this lecture. It's usually left as a self-study for students. Before we get started, I just want to point out corny joke of the day on the whiteboard. I don't really point out my whiteboard that often. I kind of like leave it in the background for you to kind of observe if you get bored or whatever during my lectures. I hope you're not bored, but this is just this is like the dad joke of math here. A volume of a pizza with thickness A and radius Z is pi times Z times Z times Z pizza. It's cute. Anyway, watch out. I might post some more stuff from time to time on that board, and if you keep your eyes peeled, I don't know, maybe you'll get a laugh from time to time. So yeah, we're going to extend to higher order. Hopefully the concepts from last video are familiar, and if so, this should not be a stretch at all. So yeah, everything that we do here is going to really depend on that last video, but also operator theory and that ability for us to like factor the D operator and so on, as we did a few lectures ago. So you may want to make sure that you review those first and you feel strong about that stuff. So we're going to be talking about nth order differential equations here, given by, well, this. So we're still homogeneous. We still have a 0 on the right hand side here. So no surprises there. We're still dealing with constants for coefficients. So constant coefficients equation, an minus 1, a1, all of these are constants. So we're going to be dealing with equations that are very similar in structure to what we did before, but the difference is that now we're going to be dealing with nth order rather than just second order. But everything that we know is already going to spill over to this. It's not hard to extend. So if you assume the same solution form as before, that's y equals e to the rx, and substitute in, you're going to get an nth degree polynomial as your characteristic equation. So with second order differential equations, you get to a second degree characteristic equation. For nth order differential equations, you get into an nth degree characteristic equation. Second order equations are easy to solve because you can always use the quadratic formula. These ones aren't always as straightforward. You might have to do a little bit of legwork to think of how you might factor something down. Theorems like ones that you might have seen in grade 11 and 12, like factor theorem, can come into play here if you're trying to find roots to these things, whether they are real roots or complex roots and so on. We're going to do a couple of examples to make sure that all of that is clear. But it flows exactly the same way. You get to that equation, you solve it for the different values of r that satisfy it. There should be exactly n of them for an nth order equation, but some of them might be complex, some of them might be repeated, and you have to be aware of that. But then once you've got them, the cases are all parallel to what we have already covered. So we're just going to dance over some of those cases and then do a couple of examples, and that'll be it. It's not going to be too hard, I don't think. So the first case is the easy case, the straightforward case. And that's the case where all the different roots you get are different and real. And in that case, you just get the corresponding exponentials. And the general solution is a linear combination of all of them. So see, e to the first root x, e to the second root x, e to the nth root x, and you add them all up and put arbitrary constants in front of all of them. That's as easy as it gets. So that's that, and we're moving right on to the second case. As I said, we're going to embed these in examples and kind of combine some things, just so you can see how they all interplay. You might have the case where some of the roots are repeated. It's possible for some of those to be repeated more than to have a, we call multiplicity of 3 or higher. We saw some cases. So for example, this differential equation, we saw like imagine if we had y double prime plus 4y prime plus y, plus 4y equals 0. This was the second order case, and we would get to a characteristic equation that's like r squared plus 4r plus 4 equals 0, and you'll recognize this as being a perfect square. This is r plus 2 all squared equals 0, and we would obtain a repeated root of r equals minus 2. We would say r equals minus 2 repeated twice. Okay, in general though, you could get that a root is repeated 3 or more times. No matter what, a repeated root, you could say that we have algebraic multiplicity. Big words, but multiplicity just means repetition of 2, and algebraic means that it satisfies that equation. It's a root. We have algebraic multiplicity of 2. And it's this case that corresponds to the second case from that last lecture. But in the case that you get even higher multiplicity, if you have that a root is repeated m times, then you need m linearly independent solutions corresponding to that root. So when we had 2, you would get e to the root times x, and then x e to the root times x. We would get these first two. But if you have higher multiplicity than even that, you get ever increasing powers of x. You can show that all of these are linearly independent from one another. But you continue up, you get x squared e to the root times x, and up to ever higher powers. So repeated m times, I would need to go up to x to the power of m minus 1, e times the root times x. So you would then take a linear combination of all of those. So stick an arbitrary constant in front of each one and add them up. Again, we're going to get to an example at the end of the day here that kind of puts a lot of this together. So that's the second case. Third case is the case that there are complex roots. So complex roots always come in pairs. If you think of the quadratic formula, you're going to be able to factor down any expression, no matter how high the degree is, into either linear factors or quadratic factors. And those quadratic factors you can't factor down anymore, that are irreducible, will give you a complex pair of solutions. So for every complex pair you get, you're going to get something like that last case that we covered in lecture number 20. And that is an exponential times a cosine and a sine function, where the alpha and the beta are the real and the imaginary parts. So that should be really familiar, especially if you've practiced a little bit with these already. And that can turn up. You can get many complex pairs depending on what the degree is. And that's a third case that we can run across. There's exactly one new case that can arise when we're dealing with these higher order equations. And it's that these complex roots could repeat. I could get a complex pair and then have the complex pair have multiplicity too. I could have a complex pair occurring twice. So that's a little bit interesting. When you get a repeated complex root though, it's kind of satisfying. We're not going to do the derivation here because it's really kludgy and really difficult. But you end up with this. You get kind of what you want to happen, thinking of what else happens with repeated roots for real. You get an exponential times cosines and sines. And if it's repeated, if you get the same alpha and beta in another complex pair, then it's repeated, you get x times the same thing. And if it happens to happen again, you get x squared times the same thing. And so on, all the way down, increasing that power of x to make sure that you keep getting linearly independent solutions out of that. You can use things like reduction of order to show this. It is very hard to do that. So take my word for it here, and you will see it in action when it comes to these last couple of examples. Okay, and the last important note here, before we jump into those examples, is pretty important. With higher order, you have the possibility of many of these things happening all at once. Perhaps with a third order equation, you get 3 roots of 3, 4, and 4. So that I have a distinct root of 3 that gets its own exponential, and then 2 roots of 4, which is Well, a regular exponential and a repeated root. So I get like an exponential, another exponential, and then x times that other exponential, and so on. I could have a real root and a complex pair. So you have to be ready to work with all of these. Okay, let's do these examples. It's not going to be too bad. Find the general solution to fifth derivative of y plus 4y triple prime plus 4y prime equals 0. So seeing that it's linear, seeing that it's homogeneous, I'm going to jump to that characteristic equation. And that is just replacing those derivatives of y with powers of r. I have r to the 5 plus 4r cubed plus 4r equals 0. It turns into a big factoring problem. I see that r is common to everything, so I'll factor that out. R times r to the 4 plus 4r squared plus 4 equals 0. I'm expecting 5 roots here because it's a fifth order differential equation. So make sure that you have those. If I try to factor this last piece down, I think I get r squared plus 2 squared. Thinking of this as a perfect square in the variable r squared. And you could multiply this back out to verify it for yourself, but I think it's pretty clear there. Equals 0. So I have r times r squared plus 2 squared equals 0. All right, let's see what this means. It looks like r equals 0 is going to solve this thing. And it's pretty easy to see that when you sub it into the characteristic equation, r equals 0 makes left side equals right side. So that's fine. The other possibility, so I'm just going to write this here. The other possibility is that this thing is equal to 0. So I'm going to write or r squared plus 2 equals 0. You could use the quadratic formula if you want, but with just the 2 there and no r term, it's pretty easy to see that we get r squared equals minus 2, which means that r is equal to, okay, plus or minus the root of 2i. Okay, so we need to think about this, and there's something else to notice as well. I only have 3 roots right now. I have 0 and then this complex pair. But it's a complex pair that happens twice. Because of this squared. I could write out that factor twice. But I could just notice that that squared is there, so it happens twice. And so this is a repeated complex root. And so I am going to want to think about that. Let's see here. There's something else about this root that's really interesting. As a complex root, I need to be able to find its real part and its imaginary part. I can see its imaginary part. It's a root 2 that's in front of the I. So it looks like the beta is equal to root 2. What's the alpha? There is no number in front of the plus or minus. So what would it be? It happens to be 0. So the alpha here is the real part of that complex pair, but it's 0. There is no real part. I have 0 plus or minus root 2i. That happens quite often, and we're going to see a lot of examples with that. So I wanted to make sure that there was an example like that that we could see. So it looks like we have 5 roots. R equals 0 is a real root. And then r equals plus or minus root 2i is repeated twice, and that's going to be a repeated complex root. Based on that, I can write down all of the different solutions and sum them up. So the solution is going to be, I can still write it down right away. I'm going to have c1 e to the 0t from the real root that's right there. And then I need to think about how those complex roots work. It's e to the alpha t, e to the 0t, and then c1 cos of the beta, root 2t, plus c, oh wait, I already have c1, so I'll call it c2, and I'll do c3 sine of root 2t. All right, that's the solution that comes from the complex root, but it's repeated twice. So now remember that the that form, what happens is that I have to have the same thing but bumped up by a power of t. So it's going to be t times the same thing. And then with new constants, c4 cos of root 2t plus c5 sine of root 2t. Of course, the e to the 0t's, I mean, we talked about it when I did the 2 lectures ago. When you have that 0 real part, or if you have a 0 real root, that really corresponds to a constant solution. And when you have a complex root with an alpha equals 0, the exponential is not really there, and you just get kind of sines and coses. So really, we could write this whole solution in this way. c1 plus, and then c2 cos root 2t plus c3 sine of root 2t plus c4 t cos root 2t and c5 t sine root 2t. You'll want to make sure that at the end of the day, you have an equal number of arbitrary constants as you did an order to the dE. And if you remember back to existence and uniqueness, we know that we would need 5 initial conditions to go with a 5th order differential equation. You would need those conditions to satisfy 5 arbitrary constants. So if you write down a solution here and it only has, say, 3, because maybe you missed the repeated root, you want to go back and check your work. There has to be 5. That's what our theory says. So that's that. There's our first example, but let's do another. Operator notation. So we want to find the general solution to d minus 3 cubed, d minus 1, u of x equals 0. So remember, when something is applied like this, we did a little bit of work at the beginning of this section to do with operator notation. So these are operators, and they're applying to the u of x. I want to say that when you have your operators factored in this way, it is a huge advantage, because essentially it's doing the job for you of factoring down your characteristic equation. So I want to write a little bit of a note about this, but when you have a dE expressed in operator notation, and it is factored down like this, that's done the work for you of actually doing the factoring problem and figuring out what the roots are. So this, I want to say literally, puts our characteristic equation characteristic equation into a similar factored form. Right? Sometimes I've had students that will see something like this, they'll write it out, they'll try to, I don't know, expand those brackets and figure out what the differential equation is, but then from there they have to find a characteristic equation and factor it all back down. And so it's like you have to undo all the work. It doesn't make any sense to do that. So here, the characteristic equation is simply, well, r minus 3 cubed, r minus 1 equals 0. If I were to expand all of those d's, which I can do because the d is a linear operator, all that kind of stuff, and then I would write out the characteristic equation, I would get an expanded form of that equation. And if I wanted to find the roots to it, I'd need to factor it back down. So why expand when you already have it in a factored form? That's key, and it's really, really helpful to be able to see that. So in any case, we have r minus 3 cubed, r minus 1, and I can solve this right away. If I present a dE to you in this way, it is a gift. It is me saying, don't you worry, I've got your back. I will tell you what the roots are, because here we have r equals 3 times, and r equals 1. We should get 4 in total because I have a d cubed and a d, so I have a fourth order differential equation here. And those are my roots. So once I have this, there's no problem. I can write out the solution. I have a one root single time. So it looks like my solution is u of x equals, I'm going to write c1 e to the, I'll get rid of the r equals 1 first, e to the x. And then r equals 3 times. Let's remember how this works. I get a c2 e to the 3x. It's repeated again and then repeated again further. I'm going to get c3 x e to the 3x. I'm going to get c4 x squared e to the 3x. And that's going to do it for my solution. 4 linearly independent solutions, all added up with arbitrary constants out front. So yeah, being able to go back and forth between operator notation and like the standard notation using primes and stuff like that can be really helpful, especially when you're dealing with equations presented like this. That's pretty much it for this section, and that will do it for this chapter. There's a lot of really good practice with the for you to try problems, so I suggest that you do it. These last topics that we got into really aren't too hard once you dive in and you try. Students tend to get really good at it because essentially they're just factoring problems where the different kinds of factored solutions lead to different looking general solutions to the differential equation. So keep practicing and let me know if you need any help. From here, we're going to be jumping into what happens when your differential equations are non-homogeneous. That's going to be the next arc of the course. That's going to be in lecture 22, which is coming up. And we're going to find that while you can just write down the solutions to homogeneous DEs without much trouble at all, non-homogeneous DEs make things much, 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 much bigger. Not necessarily super hard. I think every step will be okay, but you will have to practice. You'll want to make sure that this material is totally mastered before you move on, but then we'll explore that together. So join me, and good luck studying, and I hope to see you in the next lecture. Take care, everybody.